Welcome back. This is part 3 of the concentration code. I'm Dr. Alfred Ricks Jr. In this part, we will be covering unit conversions at the speed of thought and mental shortcuts that actually work in a code. You can find more detailed information on this subject in my book, The Concentration Code. Unit confusion is responsible for more medication errors in the emergency medicine than almost any other single cause. Not the wrong drug, not pump malfunction, not pharmacy mistakes. Units. Grams confused with milligrams, milligrams confused with micrograms, liters confused with milliliters. They happen to experienced, competent people under pressure, and they happen because the mental process of converting between units was never made automatic. And that needs to be automatic to survive a high-stress environment. The math behind unit conversion is simple. The problem is speed. When you're standing at a bedside doing a rapid deterioration, your working memory is already handling a dozen competing demands. You're tracking the monitor, you're listening to the physician, you're watching the patient's color, their breathing, their response to what's already running. In that environment, any calculation that requires deliberate mental effort competes directly with everything else your brain is trying to do. Unit conversion, when it's slow, takes up cognitive space that should be going towards clinical judgment. When it's fast and automatic, it disappears into the background, and you barely notice it happen. My goal is not to teach you unit conversion as a skill you perform, but to make it something you don't even have to think about. The tenfold dosing error is the most dangerous direct consequence of unit confusion. It happens when a clinician works in the wrong unit without realizing it. A drug ordered in micrograms gets calculated in milligrams. A dose in grams gets treated as milligrams. The arithmetic feels correct, but the numbers add up with the wrong unit system. The answer looks reasonable on paper, but the actual dose delivered to the patient is 10 times higher or 10 times lower than intended. 10 times. That's not a rounding error. That's a lethal overdose or a completely ineffective treatment, and it's invisible until the patient condition tells you something went badly wrong. Slow unit conversion also creates a bottleneck at exactly the wrong moment, and that's during a code. My mental shortcut system eliminates this delay entirely. The 5 unit pairs that cause the most trouble in emergency medicine are grams to milligrams, milligrams to micrograms, micrograms to milligrams, liters to milliliters, milliliters to liter. Every one of these conversions follows the same underlying logic, and once you understand that logic through a simple visual model, all 5 become automatic. The model is the metric ladder. The metric ladder is a one-time visual that replaces memorization forever. The metric ladder is simply the most useful mental model in clinical pharmacology, and it takes about 2 minutes to learn. Once you have it, you never need to memorize a conversion rule again. The ladder does the work for you. Picture a vertical ladder with 3 rungs. The top rung is grams, the middle rung is milligrams, the bottom rung is microgram. That's it. 3 labeled rungs, 3 units. Every drug weight conversion you'll ever need in emergency medicine lives somewhere on this ladder. The rule is simple. Moving down one rung multiplies by 1,000. Moving up one rung divides by 1,000. Just commit this to memory. Start at grams and move down to milligrams. Multiply by 1,000. 1 gram is equal to 1,000 milligrams. Move down again from milligrams to micrograms. Multiply by 1,000. 1 milligram is equal to 1,000 micrograms. So 1 gram equals to 1 million micrograms, which is just 2 steps down the ladder, each one multiplied by 1,000. Going in the other direction works just as cleanly. Start at micrograms and move up to milligrams. Divide by 1,000. 500 micrograms divided by 1,000 is equal to 0.5 milligrams. Move up again from milligrams to grams. Divide by 1,000 again. So 500 milligrams divided by 1,000 equals 0.5 grams. Every conversion is just a question of which direction you're moving on the ladder and how many rungs you're crossing. The reason this visual works better than a memorized rule is that it gives you direction. When you're under pressure and you can't remember whether to multiply or divide, you look at the ladder in your head and ask yourself one question. Am I going up or down? The direction tells you the operation. You never have to remember the rules separately from this concept because the visual contains the rule inside it. Here's a clinical example to make this concrete. A physician ordered dobutamine at 5 micrograms per kilogram per minute for a patient in cardiogenic shock. The bag you have is labeled 250 milligrams and 250 milliliters. You need to know how many micrograms per milliliter are in the bag before you can calculate the rate. Start with 250 milligrams. You want microgram. You're moving down one rung on the ladder. Multiply by 1,000. 250 milligrams become 250,000 micrograms. Now divide by 250. That gives you 1,000 micrograms per milliliter. Every milliliter of the bag contains 1,000 micrograms of dobutamine. You got there in 2 steps using the ladder, no calculations needed. The volume side of clinical pharmacology has its own version of this. Liters and milliliters sit on a 2-rung ladder with the same relationship. 1 liter is equal to 1,000 milliliters. Moving from liters to milliliters means going down one rung, so you multiply by 1,000. Moving from milliliters to liter means you're going up one rung, so you divide by 1,000. A 0.5 liter bag is 500 milliliters. A 250 milliliter bag is 0.25 liters. You rarely need to convert between liters and milliliters in a clinical emergency because most bedside work happens in milliliters, but the ladder handles it in the same way when you do it. Fast mental conversion methods for every common clinical unit. The latter gives you logic. Now let's work on the speed. There are specific mental techniques for each conversion pair you'll encounter at the bedside. Built around round numbers, anchors the pattern-based thinking so you can execute them in seconds without writing anything down. Grams to milligram is the easiest conversion in clinical practice. You're moving down one rung. Multiply by 1,000. In practical terms, this means adding 3 zeros or moving the decimal point 3 places to the right. 1 gram becomes 1,000 milligrams. 2 grams become 2,000 milligrams. 0.5 grams becomes 500 milligrams. The mental shortcut is to think of the gram number and then picture it with 3 zeros attached. For most clinical drug amounts, the numbers are small enough that this is instantaneous. Magnesium sulfate is commonly ordered as 2 grams. That's 2,000 milligrams. Amiodarone, 150 milligram loading dose, you're already in milligrams. No conversion is needed. Sodium bicarbonate, 50 milliequivalents, is a different unit entirely. But when you see it expressed as 4.2 grams, you know immediately that's 4,200 milligrams. Milligrams to microgram is the conversion you'll use most often in vasopressor and sedation management. You're moving down one rung again. Multiply by 1,000. The mental shortcut is identical. Add 3 zeros or shift the decimal 3 places right. 4 milligrams become 4,000 micrograms. 8 milligrams become 8,000 micrograms. 0.4 milligrams become 400 micrograms. The clinical anchor that makes this automatic is norepinephrine. A standard norepinephrine bag is 4 milligrams in 250 milliliters. 4 milligrams is 4,000 micrograms. Divide by 250 and you get 16 micrograms per milliliter. If you do that sequence in your head in under 5 seconds, you've got the milligrams to microgram conversion locked. Practice it with norepinephrine specifically until the number 16 micrograms per milliliter comes to you automatically when you see 4 milligrams in 250 milliliters on a label. That single pattern will serve you dozens of times per month. Micrograms to milligrams is the reverse. You're moving up one rung. Divide by 1,000. The mental shortcut is to drop 3 zeros or shift the decimal 3 places left. 500 micrograms becomes 0.5 milligrams. 200 micrograms becomes 0.2 milligrams. 1,000 micrograms becomes 1 milligram. The clinical scenario where this comes up most often is when you're verifying a dose that's been calculated in micrograms and you want to sanity check it against the milligram amount in the bag. If your calculation tells you that the patient is receiving 32 micrograms per hour of norepinephrine, you can immediately convert that to 32 milligrams per hour. Then you ask yourself, does 32 milligrams per hour make sense for a norepinephrine drip? The answer is no. That's far too high. And that sanity check just caught a calculation error before it reached the patient. Milligrams to grams is the least common conversion at the bedside, but still comes up during drug preparation and when reading pharmacy labels. You're moving up one rung. Divide by 1,000. 1,000 milligrams becomes 1 gram. 500 milligrams becomes 0.5 grams. 250 milligrams becomes 0.25 grams. The clinical context where this matters most is when you receive a drug in milligrams, but the bag is labeled in grams or vice versa. Lidocaine bags are sometimes labeled as 2 grams, and the ordered dose might be expressed in milligrams. 2 grams is 2,000 milligrams. Knowing that instantly lets you verify the bag without recalculating from scratch. Liters to milliliters is the simplest volume conversion you'll encounter. 1 liter is 1,000 milliliters. The mental shortcut is the same. Multiply by 1,000 when going to smaller units. A liter bag of normal saline is 1,000 milliliters. 0.5 liter bag is 500 milliliters. You're unlikely to need this conversion during emergencies because almost all bedside volume work happens in milliliters already, but it matters when you're calculating total fluid intake over a shift or interpreting an order written in liters. The key habit is to always convert to milliliters before you do any concentration math. Calculation concentrations require consistent units, and milliliter is the unit that matches your pump, your bag, and your infusion rate. The pattern-based anchor system works this way. It works like this. For each common drug in your clinical environment, you memorize one reference concentration using the latter, and then you use that anchor to check any new bag of the same drug. Norepinephrine, 4 milligrams in 250 milliliters equals 16 micrograms per milliliter. That's your anchor. If you get 8 milligrams in a bag of 250 milliliters, you know immediately it's double the concentration, so 32 micrograms per milliliter without doing any new math. If you get a 4 milligram bag in 500 milliliters, you know it's half the concentration of the 4 milligram bag in 250 milliliters. So the concentration is 8 micrograms per milliliter. The anchor reference point does the heavy lifting. The new bag just gets compared to it. This is exactly how experienced clinicians process concentration so quickly. They're not calculating from scratch each time. They're comparing it to a known reference point and adjusting for the difference. You can build that reference library deliberately, starting with 5 or 6 drugs you use most often, and add it to those drugs every time you encounter a new concentration on your unit. Now let's talk about how to calculate micrograms per kilogram per minute in your head without losing your mind. Weight-based dosing is where most clinicians hit a wall. The calculation involves 3 variables at once: the drug concentration, the patient's weight, and the target dose in micrograms per kilogram per minute. Holding all 3 in working memory while under pressure without a calculator feels nearly impossible at first. But the calculation follows a completely predictable 3-step sequence, and once you've run that sequence enough, it becomes a mental habit rather than a calculation. The 3 steps are always the same. Step 1, find the concentration of the bag in micrograms per milliliter. Step 2, determine the patient's weight in kilograms. Step 3, calculate the milliliters per hour that delivers the target dose. Every microgram per kilogram per minute calculation in emergency medicine follows this exact sequence, regardless of the drug, the bag size, or the patient. The steps don't change, only the numbers do. Those 3 steps apply to dopamine, norepinephrine, epinephrine, and every other weight-based infusion you'll encounter. Repeat this sequence enough time and it becomes a reflex rather than a calculation. Now, let's walk through a complete milligram per kilogram per minute calculation using this 3-step method. The drug is dopamine. The bag is labeled 400 milligrams and 250 milliliters. The patient weighs 80 kilograms. The ordered dose is 10 micrograms per kilogram per minute. What rate do you set on the pump? Step 1, find the concentration in micrograms per milliliter. Start with 400 milligrams. Move down one rung on the ladder by multiplying by 1,000. That gives you 400,000 micrograms. Divide by 250 milliliters. That gives you 1,600 micrograms per milliliter. The bag contains 1,600 micrograms of dopamine in every milliliter. Step 2, calculate the dose in micrograms per minute for this patient. 10 micrograms per kilogram per minute times 80 kilograms is equal to 800 micrograms per minute. The patient needs 800 micrograms of dopamine delivered every minute. Step 3, convert micrograms per minute to milliliters per hour. You need 800 micrograms every minute. There are 60 minutes in an hour, so you need 800 times 60, which is equal 48,000 micrograms per hour. Divide by the concentration, remember, of 1,600 micrograms per milliliter. That gives you 30 milliliters per hour. Set the pump to 30 milliliters an hour. That's the full calculation, 3 steps, each one building on the last. With practice, this sequence takes about 15 seconds in your head using round numbers. If you already have the concentration memorized for a standard dopamine bag, step 1 disappears and the whole calculation shortens to 2 steps. Now, let's run that structure with norepinephrine. The bag is 8 milligrams and 250 milliliters. The patient weighs 70 kilograms. The ordered dose is 0.1 microgram per kilogram per minute. Step 1, 8 milligrams times 1,000 is equal 8,000 micrograms. Divide that by 250 and you got 32 micrograms per milliliter. Step 2, 0.1 microgram per kilogram per minute times 70 kilograms is 7 micrograms per minute. 7 micrograms per minute times 60 minutes equals 420 micrograms per hour. Divided by the 32 mics per milliliter you already calculated gives you 13.1 milliliters per hour. Round to 13 milliliters an hour and set your pump. Epinephrine calculation for a patient. The bag is 4 milligrams and 250 milliliters. The patient weighs 90 kilograms. The ordered starting dose is 0.05 micrograms per kilogram per minute. Step 1, 4 milligrams times 1,000 is equal to 4,000 micrograms. Divided by 250 equals 16 micrograms per milliliter. Step 2, 0.05 times 90 is equal to 4.5 micrograms per minute. Step 3, 4.5 micrograms per minute multiplied by 60 minutes equals 270 micrograms per hour. Divided by the 16 micrograms per milliliter concentration, that equals 16.875 milliliters per hour, round to 17 milliliters per hour, and set it on the pump. The mental habit to build is running this 3-step sequence every time you hang a weight-based drip, even when you have a calculator available. Use the calculator to check your mental answer, not to replace it. Avoiding the tenfold trap. Recognizing unit errors before they reach the patient. The error almost always originates from one of 3 places. The first is a unit mismatch between the ordered dose and the calculation unit. The physician orders 200 micrograms of a drug, and the clinician calculates the volume using milligrams instead of micrograms. The arithmetic is correct within the wrong unit system. The result is a dose 1,000 times higher than intended. The second origin point of errors is a clinical placement error doing mental math. Moving a decimal point 1 point in the wrong direction produces a 10-fold error. Moving it 2 places produces a 100-fold error. Under cognitive load, decimal placement is the step most likely to go wrong because it requires precise spatial tracking of a number that exists only in your working memory. The third origin of errors is a label misread, where a clinician reads 1 milligram as 10 milligrams or reads a concentration of 0.1 milligram per milliliter as 1 milligram per milliliter because the decimal or the leading zero didn't register clearly. What I call the sanity check system has 4 questions you run on any drug calculation before you program a pump. First, is the answer in the right unit? If you're calculating milliliters per hour and your answer comes out in micrograms, something went wrong in the setup. Second, is the pump rate within the expected range of this drug? Most vasopressors run between 1 and 60 milliliters per hour for standard concentrations. An answer of 300 milliliters per hour for a norepinephrine drip should stop you cold. Third, does the dose per hour make sense relative to the total drug in the bag? If the drug contains 4 milligrams total and your calculations say the patient is receiving 8 milligrams per hour, the bag would be empty in 30 minutes. That's a red flag. Fourth, does the clinical picture match the expected effect? If you start a vasopressor at a calculated rate and the blood pressure doesn't move at all, moves dramatically in seconds, or doesn't have the effect you expect, the concentration or the rate may be wrong. Avoiding the tenfold trap. Decimal errors have specific patterns that make them catchable. A pump rate that ends in an unexpected string of zeros often indicates a decimal shift. A dose that seems impossibly high or implausibly low for the clinical situation is almost always a decimal error. A calculated concentration that doesn't match the standard concentration for that drug by a factor of exactly 10 is a strong signal that the decimal moved one place during the calculation. One practical technique for preventing decimal errors specifically is the round number anchor. Before you run any calculation, Estimate the answer using round numbers and note roughly where it should land. If you're calculating the rate for a norepinephrine drip and at a low starting dose for an 80 kilogram patient, you know from experience that the answer should be somewhere between 5 and 20 milliliters per hour for a standard concentration. If your calculation produced 150 milliliters per hour, you know before you even verify the math that something is wrong. The leading zero rule is a documentation and communication standard worth internalizing as a personal habit regardless of what your institution requires. Always write 0.5 milligrams, never 0.5 milligrams. The missing zero before the decimal point is one of the most common sources of misread orders in emergency medicine. When someone reads 0.5 quickly under stress, they can misread it as 5. That's a tenfold error from a single missing character. Always include the leading zero. It costs nothing and it prevents a category of errors that has caused patients' death. Trailing zeros work in the opposite direction. Never write 5.0 milligrams when you mean 5 milligrams. The trailing zero after the decimal point can be misread as 50 milligrams. Write 5 milligrams, not 5.0 milligrams. Join me in part 4 of this series on the concentration code on mental math shortcuts for any IV bag in seconds. You can find more detailed information on the subject in my book, The Concentration Code.